Okay, so welcome everybody. Thank you for being here. And thank you, Frédéric, for being with us today. So it's an honor and a pleasure hosting your class today. So Frédéric is a professor, a CNRS professor at Université Paris-Saclay in Paris, and he's gonna talk about Navier boundary conditions, sleep of liquids. So you can start whenever you want, Frédéric. You can start sharing your slides.
I will
And
try to share.
as always, people feel free to interrupt Frédéric whenever you have questions or you just want to be clear about what you are understanding. And you have just raise your hand or write in the chat. Just do whatever you want. Let's make this a nice discussion.
Yeah, so thank you for the invitation. I really appreciate to be here, and really, I really encourage you to ask questions whenever you want, because I think that I will prefer to have questions during my talks instead of letting things that are not understood. Just a first disclosure, I've taken picture and schematics from the internet. I've not always properly cited people, so I mean, well, I apologize for that. Well, so the outlook of my talk is the following. I will start, of course, to define what is a sleep length and why it is an interesting question, at least to my opinion. Then I will spend kind of a lot of time to describe the different measurement techniques that have been used and that I have used to measure sleep lengths. There are several issues that I want to emphasize for those of you who would like to work on that in the future. And then at the end, we'll take some time to discuss some of the results that we have obtained in my group regarding the sleep lengths, in particular of polymer. But I would say that it's the optional part. I would prefer to spend the most part of my talk on the first two parts. So, well, so first of all, what is a sleep length? Well, you have all learned about fluid mechanics, and you know that if you want to know how a fluid flows in a channel or everywhere, you have to solve the Navier-Stokes equations that is written here. Well, on the top of that, it is already known since the beginning that you need to solve this partial differential equation. You need boundary condition. And it's already since the early times by Navier, the question of what is the boundary condition of a liquid on a solid surface was an important question. And it's already noticed in the book by Lamb, Hydrodynamics, that some of you probably know, that it appears probably that in all ordinary cases, there is no motion relative to the solid of the fluid immediately in contact with it, which means that usually we assume that there is a no-slip boundary condition. That is the fact that the velocity of the fluid close to the solid is equal to 0, which means that we assume that the molecules adhere on the surface. Well, and a consequence of that is that if we want a liquid to flow, usually we assume that there is no interfacial dissipation, which means that the only dissipation of the liquid is in the bulk. And indeed, already Navier had very bad quality experiments to work on. He thought that when we push a liquid in a tube, the most important part of the dissipation was coming from the slip of the liquid on the solid and not from the bulk. Well, but there is a possibility of slip, and Navier already introduced this idea, and it's also quoted in the bachelor book on fluid dynamics. And the question of the boundary condition for simple fluids at the solid fluid interface has been debated for years. I don't know what happens here, but there is an issue. And the easiest way to describe a slip length or to describe the slip at the interface is to say that at the boundary, there will be a linear response, which means that there will be a stress transmitted by the fluid at the solid liquid interface proportional to the slip velocity. And the most direct way of introducing the slip is to assume, first of all, that there is a slip velocity, and there is a linear relationship between the stress transmitted and the velocity. So I will talk a lot about this Navier fluid boundary interfacial friction coefficient. The unity is Pascal second meter minus 1. And indeed, the idea is that in the bulk, you have a friction between the different layers of fluids which have different velocities, and that is the velocity, that is the viscosity. And the idea is that at the interface, you have something exactly the same. If the fluid velocity is not equal to 0, there is a stress transmission proportional to the difference in velocity between the fluid layer and the solid. Well, and then you can define several boundary conditions. So the classical non-slip boundary condition, which means that the Navier fluid solid interfacial friction coefficient tends to infinity. You can imagine some situations where you have a velocity of the fluid which is not equal to 0, but still you achieve to shear a little bit the fluid, and you have the full slip boundary condition where you have basically no shear in the fluid, and you have really a plug flow. Well, usually people who are working on slip, they are not talking that much about the Navier friction coefficient, and I would like to convince you that despite the fact that people don't use this quantity, it is the most important one. But usually people introduce the slip length, and the slip length can be defined as the following. If you are in a partial slip condition, which means that you shear a little bit the fluid, then you can extrapolate the velocity profile in the solid, and you will see that there is a distance within the solid where the linear velocity profile should extrapolate to 0. And then the slip length is divided by the distance between the real solid surfaces and the distance in the solid where you will extrapolate this velocity profile to 0. And of course, there is a mathematical relationship between the Navier friction coefficient and the slip length. Both are related, and the way to relate these two quantities is the following. So you can say that in the fluid, you can say that the stress is the viscosity times the gradient of velocity, like that. And you can estimate the gradient of velocity by simply saying that it is the slip velocity divided by the slip length. So here you have an expression for the shear stress exerted by the fluid to the solid interface. And you rewrite the Navier linear boundary condition where you say that the stress is lambda times Vs. And if you balance these two quantities, you get this relation, which is the slip length, is eta, the bulk dissipation, the bulk viscosity, divided by the lambda, the Navier interfacial friction coefficient. And here I will, or lambda is eta over beta, and usually in the experiment, people measure eta by classical rheometry, measure B by several techniques, and they extract lambda. But what I would like to emphasize is that if I look at this quantity, here you see that eta is a viscosity, is a bulk quantity, lambda is an interfacial property, and the slip length is something in between where you mix a bulk property and the surface property, whereas lambda will really be the interfacial quantity. So I would really say that if you want to have something which is more general, it's more important to discuss what is lambda instead of what is B, despite the fact that it sometimes is easier to measure B. And why is that important to measure slip length? In particular for the case of simple liquids, and indeed it's actually a very modern question. It's important because there is a lot of situations where where hydrodynamics meets nanofluidics, which means situations where you force the flow of a liquid in a pore whose size is nanometric. And in this situation, maybe the slip length becomes important. And you have this nice data by Seki and coworker, where they have studied the slip length of water in a carbon nanotube, which is the green points, or in a boron nitrogen nanotubes, which are the blue points. And you see several things which are not completely obvious. First of all, you see that the slip length of water in the carbon nitride nanotubes can be huge. It can reach up to 200 nanometers. So it's something which is even larger than the diameter of the carbon nanotube. So which means that water in the carbon nanotube will be more or less in a plug flow. And you see also that the slip length strongly depends on the nature of, it's not only a confinement effect, because in a boron nitride nanotubes, whose diameter is almost the same, the sleep length is almost equal to 0. It's not completely equal to 0, but it's nothing compared to what you have in boron nanotube. So there is this question that comes from nanofluidics, where if the sleep length becomes of the size of the tubes, these effects can be important. And of course, there are a lot of applications, and in particular, all the question of filtration of water in nanopores, where, of course, if you want to force the flow of water in very narrow pores because you want to do some ultrafiltration, as an example, the question of if you will be in a quasi flow or in the plug flow will be really important in terms of the calculation of the dissipation. So due to the huge interest of people in nanofluidics, there is an important question here regarding this quantity. Well, I have already put some values of the sleep length. So I have already said that the sleep length can be 0 or nanometrics. I mean, for all of you who have done some hydrodynamics at large scale, usually you assume that the sleep length is equal to 0. But as you have seen already, the sleep length can be in some cases measured different to 0. And I want to present you some different techniques that have been used by people in the literature. Well, I think that's the easiest way, at least historically and in terms of thinking of measuring a sleep length, is to force a Poiseuille flow in a tube and to measure the pressure drop. If you have no sleep boundary condition, you will recover the simple Poiseuille flow, which is here the relation between the flow rate, the pressure drop, the radius of the tube, the length of the tube, and the viscosity. And of course, if you have a sleep length, what you will say basically is that you have to increase the apparent radius of the tube by a quantity which is more or less twice the radius of the tube. And if you make a Taylor expansion of that, you will have that. This tells you something important, is that, well, first of all, the correction to the Poiseuille flow is the sleep length divided by the radius of the tube, which means that this effect is really important, is B is of the same order of magnitude that O. But also it tells us that if the sleep length is small, which is if it's nanometric, then if the radius of the tube becomes micrometric, then the correction becomes really small. And to be honest, the first people who have done this experiment were quantitatively were, let's say, Turaev, and what they measure it was in the 80s, and he measures sleep lengths of the order of tenths of nanometers, so 70 nanometers, which is important, and people have done this experiment later, and they all measure sleep lengths around tenths of nanometers. Okay, the difference here between L and NL in this table is that since the beginning, here I come back a little bit. Here, what I assume is I assume that the interface is somehow Newtonian, which means that I assume that lambda will be independent of the sleep velocity, or I assume that lambda will be independent of the shear rate in the fluid. And in these papers, people claim that they measure nonlinear effect in the sleep length. Okay, so that's the most important techniques, and this technique is also used a lot in polymer fluids, because in a capillary rheometer, it's exactly what you measure. You measure a pressure drop with respect to the velocity. Of course, the fluid can be non-Newtonian, so you have to take into account the fact that eta could depend on the shear rate, but it's the measurement of sleep length in a capillary rheometer is something that has been done a lot in the past. Well, another classical method to measure the sleep length is to use a classical rheometer, a plate-plate rheometer. In a plate-plate rheometer, again, if you have a sleep length, what you will have is that the apparent shear rate that you measure is not the real one, because you have to correct the gap height by the gap height plus 1 or 2 times the slip length, depending of if you assume some slip on the upper part on the lower part. And so all the math has been developed. I do not develop all the maths which are done in this paper. I tend to put the full references in my talk in order to let you work with that if you want to deal with that in the future. But the idea is that you can measure the slip length by simply measuring the torque for different various gap heights. And if you do that, there are some formulas in order to come back to the slip length within a classical rheometer. Again, I mean, the effect of the slip length will be of the order of h, which means that if the slip length is nanometric and your gap is millimetric or micrometric, then the correction will be really small. So which means that if you want to measure something with a rheometer, you need to have a slip length of the order of a fraction of the gap height. Okay. So that's something that has been used a lot by people working in polymers, and in particular in the group of Lindenarcher. Another technique that has been used a lot by people working with simple liquids is the situation where you force the flow of a fluid between a sphere and a solid surface. So you approach a sphere to a plane and you measure you measure the drainage velocity, so the force that is required to expel the liquid between the sphere and the plane. And indeed, for a Newtonian fluid, with non-slip boundary condition, what is known is that the force is proportional to the viscosity, which is clear. I mean, the more viscous the liquid is, the larger the force to drain the liquid is important. It's proportional to the viscosity. Well, that's also something clear with viscosity effect. But what is important here is that the force required to approach two surfaces diverges like 1/d, which means that if you approach more and more the sphere, the force diverges and should reach infinity. And I like to quote this experiment because it was, to my opinion, the first real experiments where people have tended to answer an important question is, to what extent is fluid dynamics valid at nanoscales? I mean, to what extent we can use the equation of macroscopic fluid dynamics when we are dealing with channels of sizes which are close to nanometers? Because then the question could be, do we measure a slip or a change of viscosity? So Chan and Hord have done that in the 80s. So they approach a sphere at a given velocity on the surface force apparatus. The plane is on a spring, and they measure how the distance d varies among time. And what they measure, they have measured two things. So first of all, when they deal with distances which are far away, basically all their data fall down on the prediction by the Reynolds force. So they say that between up to 50 nanometers of gap, classical hydrodynamics is valid. Whereas here they are dealing with distances between the two surfaces, which are 50 nanometers. And what they see is that they see a small difference between what is predicted by the Reynolds force and what is measured. So that's the difference between these two curves. That's small, but it's not in the error bars. And in that case, what they were able to do is to fit the data by changing the Reynolds formula by adding a slip length. So they just simply say that the distance between the two surfaces is d plus 2 times the slip length. And what they say here is that they measure in that case, and that case are indeed 3 cases, OMCTS, which is a small spherical surface, tetradecane and hexadecane, which are two alkanes. What they measure indeed was a negative slip length. And the negative slip length is not really a slip. What they measure in that case is a situation where there are adsorbed molecules at the surface, which means that the gap is smaller than expected. It's not a real slip, it's an inverse slip. due to adsorption of molecule. Okay, and they see that even better. So if you go at distances which are a couple of nanometer, what they see is that they start to expel 1 or 2 molecules, which is exactly the signature of this, a dead layer of fluid at the solid surface. So it's just to say that I will mainly speak of classical sleep, which are surfaces which appears to be further than the reality, but in some cases you can have adsorbed layers. And if you work with lubricants, that's the dead layer is something that you often see. Okay, so 2 messages here. So the sleep length can be either positive or negative, despite the fact that I will mainly speak about positive sleep lengths, and the fact that you can have dead layers on molecules, and also that the classical hydrodynamics work up to a couple of nanometers of gap within the fluid. Well, indeed, if you have a real sleep, the formula has to be written a little bit differently. So this formula that has been used by Chan and Nord is not the real one. It has been calculated that you have to correct a little bit the equation of motion of the fluids, and you recover the Navier equation, and you have a correction factor that depends on the sleep length. And people have used that a lot in order to study the sleep length in atomic force microscopy. And here you see as an example, that's an experiment by Craig and co-worker where they have used atomic force microscopy where they study the force between the AFM tip and the surface. And they see that the force here is lower than the predicted one with no sleep. They feed the data using this formula and they extract sleep lengths of the order of tens of nanometer usually. So that's a way people measure forces. So there are not that many measurement with the classical surface force apparatus, but a lot with the IFM. Well, indeed, I've done some other measurements in the past. What we wanted to do is to use, I mean, sorry for this slide, which is a little bit messy, but the idea is we wanted to use the same ideas as the one that we use in rheometry. So the idea is that instead of approaching the sphere with a constant velocity, we make the sphere oscillate a little bit, and we measure the force that is transmitted here on the plane in phase with the oscillations. And if you do so, exactly like in a rheometer, you can recover the force, and the force will have 2 parts. One part which is in phase with the oscillation, and one part which will be in quadrature with the oscillation. And the interest of doing that is that using these small oscillations, you increase a lot the signal over noise ratio. And indeed, exactly like in a rheometer, you can define the mechanical response or the mechanical impedance of the fluid. If the fluid is purely viscous, the mechanical impedance is only the imaginary part, and the imaginary part will be something which is proportional to the frequency and the viscosity. And again, you will have a correction factor which will take into account the sleep. So feel free to interrupt me at any time if it's not clear, but well, the idea is you force an oscillatory flow within the two surface. Yes, Michel.
Yes, why a sphere? Have you tried doing?
Why a sphere? That's a good idea. Why a sphere? It's just that it's a good question. The idea is that if you deal with small sleep lengths, and you want to have a gap which is nanometric or less, it will be really hard to have parallel surfaces with 2 planes. That's the only reason you will not be able to achieve parallelism with 2 planes, whereas with a sphere, it's when you have not this issue.
And I imagine you also have to check that both surfaces have to be very smooth.
Exactly. and that, so that's always an issue. So as soon as the sleep length becomes of the order of magnitude of the roughness, you have an important question there.
And so what's the physical effect of adding in the formula that sleep length B? So I think it's in the previous formula. So does that mean that you're practically, because I mean, if you say that the force should diverge at contact, because that's what the previous formula says, right?
Yeah,
When D is zero, the force should diverge. So adding B just prevents that, right?
adding B just prevents that. But indeed, if you properly solve the Navier-Stokes, I mean the Poiseuille, I mean no, the Stokes flow between the sphere and the plane with a slip, I
Yeah.
mean you get this equation, and indeed this equation again diverges when D is equal to zero, which means that even with slip,
Okay.
when really the two surfaces approaches, the force needs to diverge, and you don't have these if you simply correct this by adding B.
So you
Which,
do agree that you have no divergence thanks to roughness then?
no, no, no.
Okay. So it's just the presence of roughness that
No,
prevents
it's,
these
it's just a,
force.
it's, yeah, it's just a, I mean, here what I say is that if D is large compared to B, I will have the gap will be more or less the distance D plus 2 times the slip length.
Yes.
Whereas when the distance becomes smaller than the slip length, well, if I solve exactly the equation, it becomes more, I mean, I don't, it becomes more complicated,
Yeah.
and I should recover an infinite force when D becomes equal to zero.
Thank you.
And here again, yeah, as you mentioned, I assume that there is no roughness, because of course roughness could lead to an apparent slip, which is due to the fact that I don't know where to define the position of the surfaces. Well, and I just want to so here again, I wrote this for archive reasons, but here I would like to look at these curves, which is exactly what we discussed before. Here it's the inverse of the viscous damping. That should be inversely proportional to D without slip. And it's exactly what you have here for water flowing on plane Parex. Whereas if you look at water flowing on a surface which is hydrophobic, what you have is something which is a little bit different, and you have two parts. A part at large distances where simply you recover exactly the same flow, where you just shift the distance by I mean, here it's 1 times the slip length because only one surface has been selenizated. But again, if I look at distances which are really close to zero, I should recover a force which diverges. But here, what this curve says is that we are able to measure slip lengths of water flowing on OTS surfaces, and the slip lengths are around 20 nanometers, so which is small. And again, what is clear here in this experiment is that this slip length is independent of the frequency, which means that here people measured a linear response of the solid-liquid interface. So that's a classical way of measuring small slip lengths, forcing the flow of the liquid between the sphere and the plane, and it allows to measure slip lengths of very low values. So a technique that we use in my group, which allows to measure large slip lengths, is techniques where we use photo bleaching patterning. So the idea is basically the following: we take a fluid which is fluorescent, and we shine light within the fluid with a high intensity laser. And what happens in this situation is that we burn the fluorescence molecule. And then if we shear the upper plate, well, this line will be both shifted due to the shear and advicted due to the slip. And if we are able to measure these, then we are able to measure the slip length. Well, this technique is only valid if the slip length is kind of large, and it also needs viscous liquids because you need to keep this pattern a long time. So which means that you don't want the diffusion of the molecule to erase your line within time. And here you have experiment done by Marceau. So he really measured the velocity profile among different shear. And you see, but so that's the displacement of the higher plate. And you see that for all the displacement, you measure a single slip length here, which were around 200 micrometers. So here it's a large slip, and it's due to the fact that we are dealing with polymers. And I will explain later why polymer slips a lot. Leah.
Yes, I do have a question. When you're burning your molecules with the laser, does it increase the temperature locally and change the physics or not at all?
Well, I hope it doesn't.
Okay.
To test that, what we do is that we test several time of laser light, and so which will lead to different photo bleaching. So which will lead to different temperature increase, and we don't see any changes.
Okay.
But you're right. I mean, it can be an issue if we shine light too much. Good question.
Okay, thank
so
you.
That's another technique which allows. I mean, the interest here is that we are able to measure large slip lengths and with polymers, whereas these kind of slip lengths are not at all possible. You cannot measure them with a simple atomic force microscopy, because I mean, then B is so large that you don't know what you are doing with it.
Yeah, for sure.
Another technique that we have used together with Josh McGraw is we have used local velocity measurement using fluorescent evanescent wave microscopy. So the idea is that if you shine light on a solid liquid surfaces with an angle of incidence which is large enough in order that the laser light is completely reflected, you will be in total reflection, and the light will only penetrate a little bit within the liquid. And the length of penetration of the light within the liquid is of the order of the wavelength of the light, which is hundreds of nanometers. Which means that if you now add labeled particles, first of all, they will shine differently if they are close or far away from the surface. And knowing their intensity, we know how far they are, and measuring their displacement, we'll be able to measure that. We will be able to measure velocity profile in the first hundreds of nanometers close to the surface. So that's a very nice technique, because you don't need to label your fluid. You can have fluids that are not viscous, which means that you can deal with fluids such as water or not that viscous liquids. The only issue with this technique is that since you use labeled particle, to some point they can adhere to the surface and change and affect a little bit the surface, due to the fact that if they adhere, they will change the roughness of the surface and so on. But I mean, that's a very nice technique, and we had really nice experiments regarding that in the past. And here is what you have, and you see you have shiny particles, not shiny particles, which means that you are able to know where the particles are, and you are able to measure their velocity with regard to time. So that's a very powerful technique, and not that difficult to manage. What you need is a TIRF objective for microscopy, which are expensive ones due to the fact that they need really large aperture to reach this total reflection condition. But that's something that people in biology labs have often, the TIRF setup. Some more indirect measurements, but which gave very nice results. So I want to mention them. Is experiments that have been performed by Karin Jacobs, or I mean, in the group of Karin Jacobs or in the group of Karin Danloki-Veres. And the idea is to use either dewetting experiments or leveling experiments. So the idea is the following. So you make a drop of a polymer, and you heat it up. And I mean, if the polymer dewets, you will be able to measure the profile of your drop among time using atomic force microscopy. And of course, the dewetting velocity will depend on the slip a lot. So if you have model of dewetting velocities taking into account the slip, you will be able to measure sleep lengths. So it has been done a lot by Josh McGraw and others. And another technique that has been used is if you take a step of polymer like that, H1, H2, you heat it up. So this profile will, among time, flatten. And if you study the flattening velocity of this profile, it will depend of the boundary condition here at the solid liquid interface. And if you deal with thicknesses here around hundreds of nanometers, and you want to deal with sleep lengths of order of hundreds of nanometers, you have a very nice rheometer where you force a shear within a narrow gap just due to this leveling process. So there are data that I will show you later that use these techniques and that allow to measure sleep lengths of tens of nanometers to hundreds of nanometers. And of course, it only works with polymers that can be put in the glassy state. Well, so then I spend half of my time or more than that to discuss about the techniques and what is the sleep length. And I just want to tell you some results about sleep lengths and what we know for sure and what we know for not sure regarding this. Well, I think that it's interesting to spend some time on these two curves. So that's water flowing on different surfaces. Here that's real experiments, and here that's numerical simulations. So what do you see both in experiments and numerical simulations? So what is different here is that it are only the surfaces. So here you have surfaces on slippage measurements on surfaces which are more and more hydrophobic. And what you see here is that for water flowing on hydrophilic surfaces, well, you basically measure no slip. If you increase the hydrophobicity, you start to measure some slip. And to some point, it's more or less something that you can understand. The fact that what we say is the non-slip boundary condition is due to the fact that the molecule of water adhere on the solid surfaces. If the surfaces become more and more hydrophobic, the adhesion of water decreases and the slip should increase. Okay? So here's that the trends both in experiments and in numerical simulations. What is important also is the order of magnitude. Well, here are experiments that I trust because there are a lot of experiments in the literature that I don't trust, but I trust these experiments. And the sleep lengths that people measure are of the order of 25 to maybe 30 nanometers. So sleep lengths for water are small, maybe except in carbon nanotube, but on flat surfaces, sleep lengths are small. That's tens of nanometers, and which tells us that, well, if we deal with microfluidics as an example, and water, we don't care of sleep. Sleep doesn't matter. Sleep of water becomes only important if we deal with nanofluidics. Okay. Well, and here there is an important issue, is that I didn't put the experiments on the numerical simulation. And indeed, if you look precisely on both curves, you see that what do predict numerical simulation for these angles, so which is the largest angle that we can achieve with experiments, which is 110 degrees. So that's very nice OTS layer. So 110 degrees here. So numerical simulation say that the sleep is 0 or maybe 2 nanometers, but something that you cannot measure by experiments. What numerical simulation says that they predict sleep, of course. They predict sleep of tens of nanometers, but they predict sleeps of tens of nanometers on surfaces that you cannot do as an experimentalist. I don't know how to make a surface whose contact angle will be 150 degrees, which tells us that, well, trends are the same, but at least for water, the situation is messy, which means that numerical simulation do not reproduce experiments. Well, how can we go out of these messy situations? I'm completely not an expert of that, so I don't want to spend a lot of time to that, but there are some new ideas that came from the group of Frédéric Bocquet, and in particular during the thesis of Nikita Kavokin, who did an impressive work. The idea is that if we want to understand the flow of water on solid surfaces or the flow of liquid and its molecular origin, we have to take into account quantum effects. The idea, and really I'm not an expert of that, the idea is that, well, if I force the flow of a liquid, to some points I will excitate vibrations in the solids, which are phonons, and phonons are quantum effects, and the way the fluid will move and will interact with the phonons should be taken into account to get predictive effect of the slip length and predictive quantity for the slip length. So this is really new. I mean, that's a paper of 2020, and still there is still a lack of experiments where the nature of the solids, so which means the nature of the phonons that could be excited in the solids, which should be modified in order to test these ideas. But I mean, up to now, that's the only new ideas which should explain why there is such a discrepancy between numerical simulations that deal with flat and immobile layers of solids, immobile atoms of solids, and the reality. So the idea should be that we have to take into account phonons. Well, but I'm doing polymers, and part of you are dealing with polymers and complex fluids. And polymers, they can slip a lot. And this is really important if you deal with extrusion. If you want to force the flow of a polymer in an extruder, I mean, the way the slippage of the polymer will be important or not will change a lot the shape of the extruded fluid that you will have. And the slip length of polymers can be reached 1 millimeter. So when we go from simple fluids to polymers, the change of order of magnitude is really huge. And I think that, I mean, it's nice because then these slip lengths are much easier to measure. And maybe we can learn some things about slippage studying polymer. But then an important question is why does polymer slip so much? Why are polymers so different from simple liquids? And the explanation was given by De Gennes in 1979. And I must say that I'm really impressed by the fact that it's a paper in French. That's a paper in the Compte Rendu de l'Académie des Sciences. I would suggest none of my PhD students to publish any paper in the Compte Rendu de l'Académie des Sciences, neither a paper in French, but it's a very impressive paper that gives a very beautiful idea. So I should mention that. And the idea of De Gennes, indeed, he really came back to the idea by Navier, and he said, well, if I come back to the fluid of simple fluids, so we have molecules, they slip, and we can define the slip length like the ratio of the viscosity of the fluid divided by the Navier slip coefficient. Now let's imagine that I just polymerize the monomers. So I do not change anything at the surface, but the only thing I do is I'm connecting the monomers to make a polymer. If I do that, if I connect the monomer, you all know that I will increase a lot the viscosity. If the molecules, if I polymerize a little bit, I will be in the Ross mode. If I polymerize a lot, I will be in the entangled regime. So the scaling law regarding the polymer length with respect to the viscosity will be different. But in any case, if I attach the monomers, I will increase the viscosity. But the idea of De Gennes is to say, okay, but I won't change anything regarding to the Navier coefficient. The idea of De Gennes is to say, well, since the friction here is something local, I do not care to know if the things are connected or not. The K will be the same in this situation on the right and in this situation on the left. And if you make this assumption that both the Navier friction coefficient are the same, then you end up by the fact that the slip length of the fluid of monomer will be the slip length of a fluid of monomer times the ratio of the viscosity of the polymers divided by the simple fluids. And this can be huge. This can be huge due to the polymerization. And the idea of De Gennes is really that. The idea is that lambda doesn't change, but polymer only slip a lot because it has the viscosity is large. And the idea is that you have an amplification of the slip due to this increase of the viscosity. So that's interesting for, I mean, so first of all, we have to test this, but that's also interesting because it tells us that maybe we can learn something of B dot by simply changing the size of the polymer. Does that work? I mean, this has been studied again by Hilton and coworkers, and I really like this curve. I mean, so that's the slip length in micrometers. So look at that. See, here it's 100 of nanometers, and here it's already almost 100 of micrometers. So first of all, that's polystyrene, different molecular weights, and they see as predicted by this equation by the gen, they see an increase of the slip length regarding the molecular weight. And they also say that they have two regimes, a regime at small molecular weight and a regime at large molecular weight. And this is due to the fact that in this regime, you are in the Ross mode, which is the viscosity of the melt increases linearly with the molecular weight, whereas here you are in the entangled regime, and the viscosity of the polymer melt increases like the molecular weight to the power 3 or 3.4. So they have two sets of experiments, and here they use another set of experiments where they measure much lower steep lengths, and this is due to partial adsorption that I will discuss a little bit later. Okay, so now we understand why polymer melts slip a lot. It's just an effect of the increase of the viscosity due to the fact that if you untangle, the viscosity increases. Yes, Michel.
So would numerical simulations in this case be able to capture the correct slip velocity, or no?
Yes. I mean, numerical simulations work quite well in this regime. I mean, it's really. I mean, as you probably know, it's really hard to make numerical simulation up to the entangled regime due to the time it required. But in the Rouse regime, it works.
Okay.
Okay, so that's it.
There is also a question in the chat from Anand Tabore. Does the solid line represent the viscosity ratio?
Does the solid? Yes, exactly. It's more or less what it represents, Alan. And in this curve, not in this curve. Here, that's another model that I want to develop. Well, I think that I should spend some time regarding polymers because I mean I'm sure that a lot of you are interested in polymers. There's an issue with polymers, which is that one. Sorry. Yes. So that's experiment done by Marceau and No. So that polystyrene solutions flowing on silica. So it's a little bit more complicated than just a melt. So you have a solvent here, but here it's a slip length he measured. So using the labeling, the fluorescence labeling technique. And here he has made some experiment where he has put the polymer solution in contact with silica surfaces 1 hour. He has done the same experiment when he puts the solution 54 hours in contact with the solution, 61 hours, and different times. Well, what do you see here is that you see that, let's come just back to these. When he lets the systems in the polymer solution in contact with the solid surface, so that's the slip length with regard to the shear rate, and he basically measured two regimes: a measure at low shear rate where the slip length is low, and a measure at large shear rate where the slip length is high. And he measured a strong transition at a given shear rate. And the position of this transition, which is here in this curve, varies among time. And there is an explanation for that, and this explanation is known since years, but you have to keep that in mind if you have some issues with slip with polymer. The idea is the following. The idea is the fact that when you have a chain of polymer chains can strongly adsorb on polymer surfaces due to the fact that as soon as they are attached by several points, if you want to detach them, you have to detach all the points at the same time, which means that basically when the adsorption is strong enough, polymers that are adsorbed at the surface, they will never desorb. But when the polymers are attached to the surface and do not desorb, potentially what they will do, they will be able to entangle with the polymer melt. So they will avoid the polymer fluid to slip. And if you want the fluid to slip, what you will have is you will have to stretch the molecule strong enough in order to disentangle the molecules which are attached to the surface by the shear. So these explain two things. These explain the fact that, first of all, there is a critical shear rate. You need to shear sufficiently in order to disentangle the polymer chains that are adsorbed to the surface with respect to the flow. And the critical position here will depend on the time, because if there are only a small number of molecules which are attached, it's easy to disentangle them. The more and more molecules are attached, you have to reach higher shear rate. And it's exactly what it says here. And the theory of this effect has been studied by Brochard and Ashdari in the 90s, and there have been several experimental verification of that by the group of Liliane Léger at the end of the 90s. And then the reason why Hilton and co-workers measure different slip lengths with regards to two sets of experiments is the fact that the shear rates that are achieved in an experiment of dewetting the brown points and the shear rates which are achieved in a leveling experiment are not the same, which means that the brown points are in the regime of strong slip, whereas the blue points are in the regime of low slip. Okay, so you have this strong effect. So now let's imagine that we are not in this regime of where we have issues with the adsorption of chains. The idea is can we get an idea of the molecular origin of the slip with polymers? And to understand that, we have performed some experiments with Marceau and No. So that's PDMS flowing on the short PDMS in order to avoid attachment. So there is short layer of PDMS to protect the solid surface. And you see several things. So you see that, well, at low shear rates, you have the problem of adsorption. At high shear rate, you have the strong slip with a small shear rate effect on the slip length, a small shear thinning effect. And this small shear thinning effect is simply due to the fact that we have also shear thinning in the bulk. So if eta in the bulk depends of the shear rate, then the slip length should depend on the shear rate. So that's the reason why. So let's concentrate on the right part. And sorry for that. And here that's the experiment of Marceau, and what he measures, so that's a log-log plot. That's the shear rate, the slip length as a function of the viscosity. You have almost something with a slope of 1, which says that, as predicted by Dejean, and that has been already predicted, the slip length is proportional to the viscosity. And since everything is a single line, it tells us that the K value is independent of the polymerization index of the polymers. Okay, here you have several polymers. But now the question is, can we get an idea of what is K? And to do so, we have made some other experiments where we have, that's now a solid experiment where we study the friction of, it's not reticulated, it's cross-linked elastomer of PDMS sliding on the same solid surface, on the same passive PDMS layer. So in that case, so we have an elastomer. So that's the same PDMS. The only difference is that it's cross-linked, and we measure the force in this sliding experiment, and we measure the stress which is proportional to the velocity. So again, it's a log-log plot. The slope is 1, so which tells us that the stress is proportional to the velocity, which is not the case. I mean, in classical solid friction, usually the effect of the velocity is small, but here, since it's not, I mean, elastomers are not classical solids, it's a little bit different. And what is nice here is that if I put the experiment of the solid frictions that you have seen before, which are the gray point, and the experiment of the slippage of liquids, which are the color points, in a plot where you have the stress at the interface as a function of velocity, everything follows the same line, which tells us that the value of the K that you measure in the slip experiment is the same as the value of slip that you measure in the friction experiment. And this is, I mean, this is more or less clear because at the molecular level, an elastomer is a liquid. So if the friction is something which is really local, it's not surprising that you measure the same value, despite the fact that it hadn't been never done before. Okay, and what is nice is if you look at the order of magnitude of this coefficient, you can have an idea of what it is. Since we have sliding PDMS on PDMS, this friction coefficient is the one that you will obtain if you use the Rouse friction coefficient. If you use the Rouse friction coefficient, that is the friction coefficient acting on a monomer, you will say that, well, the K value should be this Rouse friction coefficient divided by the area of a molecule. And the order of magnitude that you get by using these values that you get from rheology and these values that you get from slippage experiment is the same with the factor of 2, which really tells us that here we are really able to probe the monomer friction. Okay, so here at least, I mean, these molecules are mobile, so we are probably not in the same exactly in the same situation than the one of water. But with this simple experiment, we are able to give a molecular origin of the slip. Maybe if I can take 5 to 10 minutes more, and is that okay? I would discuss another effect. I mean, in order to probe the molecular origin of friction, we had the idea that it could be interesting to change the temperature, to have the idea of what will be the effect of temperature with respect to slip. And we have done that both in experiments in numerical simulations, but for pedagogical purpose, I wanted to present first the numerical simulations. Because numerical simulations are simple. So the idea of numerical simulations is you put a fluid. So now it's not a polymer. You put a fluid. You solve the equation of motion of the molecules, and you measure the velocity profile. You measure the slip. So we use a simple Cobb-Anderson liquid. So the simple idea is that that's the simplest liquid that we have in mind that do not crystallize if we lower the temperature. Problem with Lennard-Jones fluids is that if you lower their temperature, they crystallize. So we use bi-dispersed fluids in order to avoid the crystallization. And what we can do with this system is we can change the liquid-solid interactions. And well, so we do the experiment. So that's real numerical experiment. We shear the system, we measure the velocity profile, and you see in the velocity profile that where the velocity is normalized by the velocity of the upper plate, that there is a shift, and this shift is the characterization of a slip. So we can measure the slip in numerical simulation. So we measure the slip velocity, we know the stress, so we can know the viscosity, so we can measure everything in numerical simulations. So what do we have? I mean, I just want to say that, well, here in this situation, we have the viscosity with in the log scale with respect to the inverse of the temperature. And we see that if we are far above the glass transition temperature, the viscosity is an Arrhenian process, which tells us that the viscosity, I mean, looks like that. with epsilon is the activation energy of the fluid. What is nice here is that we measure the friction coefficient again with respect to 1/T. So again, we are far above the glass transition temperature. We studied also something close to the glass transition temperature, but it's not, I mean, it's not that general. And you see that again, the Navier friction coefficient can be modelized by an Arrhenius law. And we can define, exactly like in the bank, an activation energy for the friction. But if we combine these two equations, since B is the ratio of the viscosity divided by K, what we get at the end is that the friction, the slip length is an activation energy, but with an activation energy which can be either positive or negative, depending on the relative sign of epsilon viscous or epsilon friction. And it's exactly what we measured indeed in the simulation. Here we have B now with respect to 1/T, and we see that in sometimes B decreases with respect to the temperature, whereas in sometimes B increases with the temperature. And indeed, in the literature, it was completely messy up to this work because people were saying, well, B increases, B decreases with respect to the temperature. And the only reason there was this kind of strange behavior is that B mixes the bulk and the surface properties, which can have different activation energy. And we showed that it's possible in this simulation to continuously vary the sign, I mean, the value of this difference by changing the liquid-solid interaction. Okay. And what did we observe in our experiment? So that's again, that's PDMS flowing on PDMS. I mean, PDMS flowing in PDMS, that's this one. PDMS flowing on OTS, that's this one. So again, we were able to measure an activation process in the experiments. I mean, experiments are harder than numerical simulation to some points, but it was possible to show that the experiments were compatible with the experiment. And what is nice is that we understand also why the effect of the temperature on PDMS flowing on PDMS is really low, because in that case, we expect that these two activation energies should be almost the same, which will lead to an effect of the temperature on B really small. Okay, I think that I'm more or less over, so that I will switch to the concentration. I mean, I just want to say that if we deal with polymer solutions that are interesting in many situations, the question of what we define with the slip length is important, because in that case, we don't know if the concentration of the fluid close to the surface is the same than in the bulk. And if we deal with polymer solution, and if we have, as an example, a depletion of the polymer close to the surface, what we will have at the end is a layer of water, which has a low viscosity, a fluid with a higher viscosity above, and everything will look like a last slip. And indeed, it's not a real slip. It's just due to the fact that we have a layer close to the solid, which has a lower viscosity. So, I mean, I skipped to the conclusion. I was not so far to the end. What I want to let you in mind that as a take-home message, first of all, that there are a lot of techniques to measure the slip length, and all these techniques have advantages and disadvantages, and depend on the slip length you want to measure. In particular, if you want to measure a slip length which depends on the shear rate, and you use a rheometer, then there is an issue. If you use a plate-plate rheometer, the shear rate is not homogeneous in the gap, and then you have to make some hypothesis in order to analyze the data. So take that in mind. The molecular origin of slip is still an open question in some cases. There is a question of this quantum effect. Take into account that slip length is a combination of the viscosity and local friction, which means that, I mean, defining slip length is not always a good idea. And in particular, polymer slips a lot just because they are viscous, but there is nothing particular with that. It's just an amplification due to the viscosity. That friction is local. And the idea is that there is this temperature dependence that could be a nice tool to probe the molecular origin of sleep. And in particular, in system where quantum effect could be important, the temperature could be a very nice tool in order to test this quantum effect. Well, there are still a lot of open questions that, I mean, I'm working on, but you are open to join because there are much more than what I can do. The question is, what will the glass transition do on sleep? I mean, when we reach the glass transition, the viscosity diverges more than the Arrhenian process. So is the glass transition temperature of the bulk the same as the one at the surface? Probably not. So what happens in that case? The question of, well, how we can play with the molecular interaction in order to increase this depletion layer or decrease this depletion layer in the case of sleep. And of course, something which is really important and I didn't talk at all about that is what are electrostatic effects regarding to sleep. A major issue is that if you have electrophoretic effects such as the Debye length, you will have an increase of the sleep length, molecular sleep length due to this. But with charges, everything is possible, and there is a lot to do. With that, I have to thank the students in particular that work on this subject: Suzanne Lafont, Marion Zelka, Marceau Hainaut, Alexis Chenevière, and Gabriel Guyard. You saw all their curves. I mean, I try to quote them regularly. Liliane Léger, Elisabeth Charlet, with who I've done an experiment, a lot of experiments, and sorry, Gabriel Guyard, and Sami Merabia and Laurent Joly, with who I have done the numerical simulations. I mean, sorry, with who Suzanne Lafont has done the numerical simulations, and we are really nice partners, and the ANR who funded this study, and of course you for your attention. Thanks a lot.
Thank you, Frédéric. I have to say it's been very, very pedagogical, at least for me. I hope it's been also for everybody else. But yeah, very nice presentation. Everything was very, very clear for me. So people, do you have any questions? I mean, it's been very pedagogical for me because you answered the questions I had in mind, like
all
30
the time.
seconds. Yeah, like it was,
Thanks.
you were triggering questions in my mind and you answered them.
No, I know. I mean, it's late in Europe. I'm okay not to have more questions. You already asked questions, but really feel free to ask questions if you have.
Not hesitate.
It won't be the case. People are shy.
People are
Yeah,
shy. They shouldn't be.
And there was a lot of information in my slides. I mean, I can share my slides. There is no issues with that. I mean, if you are asking for that.
Oh, that's very cool.
Thank you.
I don't know if you share the slides on your website or you can write me an email and I will share the.
That's usually what we suggest to people. We just think it's easier for people to just directly write an email, send an email to you and ask for the slides.
Because I try to put references among my talk to help people who want to have more details on some parts.
I mean, also this quantum effect seems to be very interesting. I guess I will have to read the PhD thesis of this person.
Yeah,
I mean, is it a PhD?
Yeah, it was a PhD. It was a PhD.
Yeah, okay.
And I mean, the idea. I mean, the idea is really interesting. The idea is to try. I mean, in solid friction, people have no somehow joined are no taking into account how the phonons are important to describe the solid friction. And the idea is that in the liquid solid friction, this effect should be important or not. And the or not depends on the Q vector, the modes that are available in the solid and in the liquids, and probably by changing the modulus or the hardness of the walls, you can be in a regime where these quantum effects are important or not.
And do you think it can also have an impact on the friction, on the solid friction?
Yeah, I mean, these quantum effects, they are known to be important in solid friction. So I mean, it's more or less the transfer of these ideas to solid liquid friction.
Okay, but okay.
In solid
Okay,
sinusoid friction, that's clear. Thanks,
Okay.
Alan.
Okay.
Yeah, and for the glass transition and so on, do we have criteria in order to go from the liquid phase to the glass phase, or not at all?
Yeah, I think that, I mean, I think if there are some, I didn't show that, but there are some nice experiments now by again by the group of Frédéric Bocquet and by Mathieu Lizet. I should quote him because he did the experiments. Mathieu studied glycerol, which is a fluid which is really nice because you can easily reach the glass transition. I mean, it doesn't freeze. I mean, he's a very nice glass maker, and what he observed, he observed a non-monotonous behavior of the Navier friction coefficient with respect to the temperature. And all what I mean, if I come back to what I said here, I mean, yeah, here the only model I have is that I expect that if I increase the temperature, I increase the mobility, I will decrease K. And he observed a non-monotonous value of K. And one of the ideas will be the fact that that's the signature of this transition where from a regime where you have to deal with the glass transition temperature and a regime where you don't have it, or maybe the quantum effects.
Okay. Oh yeah. Again, the quantum effect.
Okay. So if there are no more questions, I'm going to stop the recording here.